How you doing, guys? Welcome to another video. This is still Redox Processes, volume number 5, What are electrolytic cells? Let's go. Okay, so volume number 5, What are electrolytic cells? We look at construction, reactants, and products. The IB understandings focus around electrolytic cells and how they work, and also identifying the reactants and products at the anodes and the cathodes. We look at the construction, explanation of how current is generated, and then we look at distinguishing between electron and ion flow in the circuit. So, the passage of electrical energy from a power supply, such as a battery, through a conducting liquid is known as an electrolysis process. And they have a variety of applications. Now, a battery has a negative terminal and a positive terminal. And if we pass electricity through, we also need to identify the negative and the positive. Now, the negative in a cell diagram is the short little fat one. And electrons originate from the negative terminal. They're pushed out of the negative and drawn back into the positive. Now, during electrolysis, electrical energy is converted into chemical energy, and the reactions that occur are kind of the opposite to voltaic cells. Because we need to generate electricity for this process, it's a non-spontaneous reaction. So a voltaic cell is a spontaneous reaction. When we connect them up, they go straight away. An electrolytic cell is non-spontaneous because we're providing the energy. A voltaic cell produces electricity. It's used to generate a current, whereas an electrolytic cell produces chemicals. And most of the chemicals that we produce via electrolysis are actually hard to come by from other means. So we use the electricity to get out our products. So in an electrolytic cell, oxidation occurs at the anode, which is now the positive electrode, and reduction occurs at the cathode, which becomes the negative electrode. Let me explain that. Electrons come out of the battery and they're pumped into the negative electrode. Now, that's decided on because it's connected to the negative terminal of the battery. The battery forces that electrode to be negatively charged because it's connected to the negative terminal. So what that means is there's a whole bunch of electrons being pumped onto that electrode. So essentially, it's got a whole lot of electrons that can undergo some chemistry. So that means that it's adding electrons to that electrode so it can undergo reduction. At the other electrode, well, we're pulling electrons out of that electrode. It's positively charged because it's connected to the positive terminal of the battery. And because we're drawing electrons out of that electrode, it's going to be the anode because the anode is loss of electrons. Now, in our solution, we have a molten solution, and molten just means that there is no water around. So here we have a molten solution of KBr, potassium bromide. So that means we have potassium ions and bromide ions. Now, what's going to happen here is those ions are going to be attracted to the oppositely charged electrode. So the potassium is going to migrate towards the negative electrode, and the bromide is going to migrate towards the positively charged electrode. So what's going to happen? Well, how is the current conducted in an electrolytic cell? Well, the current is conducted because the battery pushes electrons into the negative terminal and pulls them out of the positive terminal, but electrons can only move in the wires. So what allows the solution to conduct a current is the migration of ions in the liquid. So in this case, the potassium ions migrate towards the negative electrode, the bromide ions migrate towards the positive electrode, and that migration of ions allows a charge to flow. So the electrons move in the external wires forced by the battery, and the ions move in the solution, which completes the circuit. We don't have half cells for an electrolytic cell, it all occurs in one beaker. So solid sodium chloride does not conduct electricity when it's a solid. However, when an electric current is passed through molten sodium chloride, a chemical reaction is clearly observed. A shiny bead of sodium is produced at the cathode, and chlorine gas is evolved at the anode. Draw a diagram of an electrolytic cell representing the electrolysis of molten sodium chloride using inert electrodes. Okay, so we have to draw a diagram and then we need to label it up. So the first thing we need to do is we only have one beaker for an electrolytic cell, so it all takes place in one beaker. So here I have my beaker. The next thing I've got to do is put in my electrodes. Here we're told we're using inert electrodes, so they could just be graphite electrodes or they might be platinum electrodes is another option. In my solution, I have NaCl liquid. I need to identify my battery. The short little fat one is the negative terminal, the long skinny one is the positive terminal, and my liquid contains sodium ions as a liquid and chloride ions as a liquid. It's a liquefied salt, which means we would have to heat it up to get it to form a liquid. Now the battery dictates what charge those electrodes are. So the electrode connected to the negative terminal is the negative electrode. The positive electrode is connected to the positive terminal. Now reduction will occur at the negative terminal, and that means that it will be the cathode. Remember the saying, an oil rig cat. Oxidation will occur at the positive electrode of an electrolytic cell, which means that it will be the anode. So the difference between voltaic and galvanic is that the charges on the electrodes have been swapped over, but the process is still the same. Reduction always occurs at the cathode, oxidation always occurs at the anode. So in the solution, the ions will be attracted to the negatively charged electrode. So the sodium will be attracted to the negative electrode, the chlorine to the positive electrode. So what will be the reaction occurring at the cathode? Well, we'll have sodium ions that will form sodium metal. So you have Na plus turning into Na, in this case, liquid. So to balance that chemical equation, we need to have one electron on the left-hand side. It's going to undergo reduction. At the anode, we'll have chloride ions forming chlorine gas, and they told us that in the question. Now I need to balance this up using cohes, so I need to have 2 chloride ions and 2 electrons on the right-hand side. It's oxidation because it's occurring at the anode. So our overall chemical equation, what we would have to do is we would have to multiply the sodium equation by 2 to balance for the electrons, and then we can simply put those 2 equations together to get our overall reaction. 2 sodium ions plus 2 chloride ions goes to 2 sodium metal plus chlorine gas plus Cl2 gas. So just remember, the negative electrode is dictated to by the battery. That is where reduction occurs in an electrolytic cell. The positive electrode, that is dictated to by the battery, and that is where oxidation occurs in an electrolytic cell. They're the opposite of the voltaic. Now, if we were asked to identify the oxidant and reductant, we still apply the rule, if you're murdered, you can't be the murderer. So sodium undergoes reduction, so it must be the oxidant, sodium ions. Chloride ions undergo oxidation, so they must be the reductant. That thing does not change. Okay, volume 5, some top tips. Remember that those electrons can't swim, they're just in the wires. Remember, an oil rig cat. And when we're dealing with electrolysis, it's a liquid. It's a molten solution. There's no water. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe for more, and I'll see you